Hi guys, now we're going to start with analysis of beams. You need to understand the basic difference between a bars and a beams. A bars is a structural member whose cross-sectional will be varying throughout the length. Okay, it might be because for a step bar, through some extent of the length, the cross-section will be different, and for the remaining length, it will be different. But for a beam, if you just have a look at it, this is the length of a beam. Throughout the length, okay, the cross section will be same. So that is the main characteristic of a beam. And a beam is a structural member which carries always transverse load, means a load which is acting perpendicular to the length. Okay, so these are the two characteristics of a beam. On this beam you can see there are two different types of loads. Which are those? Means a point load, this is a 10 kilonewton, and the 10 kilonewton over here, these are the 2 point loads, and this is a uniformly distributed load. And you have two diagrams over here, one is a front view, other one is a side view. In the side view he has given the cross sectional area of your beam, that is how much, 30 mm and 40 mm. And look at this diagram carefully, he has given all the dimensions in meters, but the cross section has been given in mm. So ensure that you are converting these to meters. Okay, now before going to this, how am I going to create a finite element model for this one is, because this is the actual model or the geometrical model. Now we need to create a finite element model. So for creating that, what you need to do is follow the same procedure. Drop the lines from the ends. Okay, from this end also you just drop a line, just drop a line and leave it. Okay, then what you're going to do is place the nodes at the ends. Okay, place one node at this end. Okay, place one node at this end, and place one more node. Before that I'll draw a line. Okay, by drawing a line, straight line. Okay, just draw a straight line and place one more node at the other end. Okay, place one more node at the other end. Now since the cross section area is same throughout the length for this particularly beams, the point where exactly this 10 kilonewton is acting, from that point you just drop a line. And meanwhile the point where exactly your uniformly distributed load has been starting, drop a line, and where exactly it is going to end, so drop one more line from that end also. Okay, at the interface between the horizontal line and the vertical line, you just keep on placing the nodes. Okay, this is one intersection what you are going to see, and this is one more intersection with the horizontal and the vertical line. Place one more node and place one more node at this location. Okay, and give your node numberings, and say give your node numberings from your extreme left. So this is node number 1, and this is node number 2, and this is node number 3, and this is node number 4, and this is node number 5. And consider extreme left node as your reference. Okay, when you consider that as your reference or origin, so the coordinate values for that node will be 0, 0, 0, 0. And in order to reach from node number 1 to 2, you need to travel only along x direction. Okay, but how much distance you are going to travel? Only in x direction, that is 5, 0. Okay, meanwhile in order to reach from 1 to 3, you are going to travel in only x direction, that to how much distance? By 10 meters. Okay, close the node. And node number 4, from 1 to 4 you're going to travel a distance of 20, 0. And at node number 5, from 1 to 5 you're going to travel a distance of 25 meters along x direction, and y direction you're not going to travel, it is 0. Okay, so this is how a finite element model will be created, and this is element number 1, this is element number 2. Club two nodes. Okay, club node number 1 and 2 and form an element. Club 2 and 3 form element 2, element number 3 and element number 4. So there are 4 elements and 5 nodes. Now I'm going to try to create this in my software, and I'm going to solve this problem. So before that, go to preferences, click on structural, you choose H method. Okay, and go to preprocessor, element type, add or edit or delete, add. You have to choose beam element, 2D elastic 3. Okay, close this one. Then go to real constants, add or edit or delete, add. Okay, be careful when you are entering the real constant, ensure that he has given in mm. I'm converting that into meters, so 40 e bar minus 3 meter, mm will be converted to meters, and 40 e raised to minus 3. So where your area will be converted from mm square to meter square. Meanwhile b is base is 30 e raised to minus 3 multiplied with 40 e raised to minus 3, because I am converting that to meters, 3 divided by 12 and convert the height also in terms of meters, 40 e raised to minus 3, and whichever the values you don't know, you please do not enter any of the values. Okay, okay, close that one. So this is how you're going to do this. Material models, structural, linear, elastic, isotropic. Young's modulus is 200E9. Why am I giving like this? I am going to show you the diagram. 0.3 is a Poisson's ratio. You look into this. The Young's modulus is given as 200 GPa. So 200 GPa means giga means 10 to the power 9. Pascal means Newton per meter square. So that is why I have entered my value in terms of meters. Okay, exit. So material property has been entered. Then go with modeling, create, nodes. Click on inactive CS. Node number 1. If you just do not enter any values, by default it will be taking as 0. Node number 2. So what are the coordinates? 5, 0. Apply. Node number 3. 5 plus 5. Okay, it does 10 meters. Apply. Node number 4. 5 plus 5 plus 5. 10. That is 15 or 20. Just let me check. Okay. 5 plus 5. 10. And that is 10. Okay, node number 4 is at a distance of 20 mm. Okay, inactive CS. Node number 4 is at a distance of 20 mm. Apply. You can see the nodes have been creating. And node number 5, 20 plus 5, 25. Okay, when you are entering the last node, you are going to give it as 5. Go to elements, click on auto numbered through nodes, select 1 and 2. Sorry, in order to unselect it, right click. Okay, the cursor will be reversed, and again plus the right click, it is going to come into the position. 1 and 2, apply. 2 and 3, apply. 3 and 4, apply. 4 and 5. When you are entering the last element, you just give OK. By chance, if you give apply, you click on cancel. Auto numbered through nodes. My element is done. Next, what I am going to do is, modeling is being done. Now I am to go for applying the loads. Define loads, apply. Structural, displacement, on nodes. Select node number 1, give OK. All degrees of freedom. Select all degrees of freedom. Then you select node number 3 and 4, give OK. You choose along y direction because it's been provided with the roller supports. Okay, look at the diagram carefully. See, it has been provided with the rollers, means when you pull the beam, it is free to move along each direction. So that is why roller support. So that is why you have to support it only along y direction. Got it? Next, after fixing this, you are going to go for the point loads will be applied using the command force or moment. Okay, click on nodes, select node number 2 or 5. You can select both the nodes at a time because the magnitude is same, so that you can select both the nodes at the time, or you can choose it at different. Since if the magnitude is different, you need to choose the nodes differently. Okay. Minus. Why am I giving minus? Because it is moving towards a negative x direction, negative y direction, so it is going to be given. Then you can see that between, look at the diagram carefully, between node number 3 and 4 you are getting the you are getting this uniformly distributed load. So I need to apply that. Go there, go for pressure. Okay, you are going to choose on beams command. You choose on beams, give OK. Okay, pressure value 2 kilonewton is there, so 2 E3 and 2 E3. Now you can ask me, what is this node I and what is this pressure value at node 3? See, pressure value at node I is nothing but what is a value of load at the starting node. J means what is the value of UDL at the ending node. Okay. I think I haven't applied. Sorry. On beams. Select this one. Yeah, okay. So 2 E3 because converting kilonewton to Newton. 2 E3. Yeah, this is how you are going to apply. That's it. This is a pre-processing stage. Okay, if you just compare, look at this diagram carefully and look at this diagram carefully. Okay, I have created our equivalent finite element model for this one. Now go there. Now you are given all the values for the calculations. Now click on solve button, current ls. Okay, your solution is done. If you are encountered with any of the problems, that dialog box will be showing where exactly the corrections has to be made. Go to general post procedure. In the general post processor, you straight away go to element table, define table, add. Okay, as usual, scroll down, select by sequence number, you choose SMSI2, apply, scroll down, choose SMSIC6, apply, choose by sequence number 8, apply, scroll down, by sequence number 26812, apply, again come down, by sequence number, now I'm going to choose NMIC 1, apply, choose by sequence number NMIC 3. Okay, now why exactly these commands, I'll let you know, because the output what exactly we need whenever we want to do the analysis of beams, the output what we need, that is also should be known for a person. Okay, see, whenever we are going to do the analysis of a beam, our output required is a shear force diagram, bending moment diagram, and bending stress distribution and the deflections. Okay, now what you are going to do is go for nodal solution, click on DOF solution, choose Y component of displacement. Okay, so you are going to get the deflection. Okay, you are going to get the deflection of the beam. Now again click on this element table data. When you choose 2 and 8, you are going to get the shear force value on the beam. Okay, again click on the same element table data. Okay, select 6 and 12, you are going to get the bending moment diagram values. Okay, if you click on the element table data, if you choose 1 and 3, NMIC 1 and 3, if you just give OK, so these are the values of stresses. Okay, which will be in terms of Newton per mm square. If you just convert it, this is 2 gigapascal and this is 0.17 gigapascal. Okay, because every value you have obtained in terms of Newton per meter square. Now click on the reaction solution. Okay, click on the reaction solution, choose all items, you are going to get the reaction table. You need to copy down this one. Okay, copy down this table as usual, copy 1, 2, 3 and 4, copy down 4. So how many tables you need to copy? This is BMD, this is bending stress, maximum bending stress 1 and 3, 6 and 12 is for your BMD, and you look into this. 2 and 8 is for your SFD. Okay, next go for plot results, click on contour plot, click on nodal solution, again click on DOF solution, you choose Y component of displacement, you're going to get a diagram. Let me show you. Yeah, let me send remaining so this is the interpreting the results is one of the biggest tasks over here. See, what is this? Node number 1, the displacement is 0. Yes, because it is completely fixed. At that point you are not going to get any of the deflection. You should not call it as displacement here, you need to call it as deflection in case of a beams. Okay, at node number 2 you can see you're going to get at a distance of 5 meters from this point. Okay, at that node number 2 you are going to get 2.32 meters. Okay, you need to understand that is 2.3251 meters. Since at node number 3 and 4 we have given a support along Y direction, so you are not going to get any of the nodal deflections at that point. And at node number 5 you can see that is at the free end. Okay, you are getting a displacement of 27 meters, which is a huge displacement over there, huge deflection. Okay, then you click on the line element results, or you can click on the line element results, you choose 2 and 8. Okay, in the first drop down list there should be 2, and in the second drop down list it should be SMSI 8. Okay, see, this is how the shear force diagram is going to vary. Now I'm going to show the interpretation, how exactly I want to do. This is 6 and 12, and I think this is 2 and 8. Now you can see element number 1. Okay, what is this SMIC2 means? The value of shear force at the starting node. What is this 8? Value of shear force at ending of the element. Okay, so this is how you're going to receive. For example, element 1, what is the shear force value? That is minus 6.071 minus 6.071.4. so that is 1. So minus, because minus means it is going to come in the downward direction, so minus 6.071.4 minus 6.071.4 Newton. The unit is Newton. And for your element 2, it is going to start from 3928, so that is positive, so that's going to go upward direction, 3928.6 Newton, and it is going to end at the same value, so 3928.6. For your element 3, it is going to start at minus 5535, that is at this location, and plus 14,464 Newton, that is at this point. So this is how you need to interpret the results. In the same way, okay, click on the 6 and 12. Okay, 6 and 12, you're going to get your bending moment diagram. The same way you need to do the interpretation. Okay, 6 and 12. Say for example, I'm going to show for only element 1. See, for your element 1, it is going to, the 6 means the value of bending moment at the starting node of that element 1, and 12 means, SMIC 12 means the value of bending moment at ending node. So if you have a look into this, see, you can see this white line, that is where your element 1 has been ending. Okay, now this is going to start at this point is minus 16.071, so that is why it is coming in the downward direction, and it is going to end in a positive. Okay, so that is why 14.286. In the same way for your element 2, okay, where it is going to start at the 14.286 and it is going to end somewhere here, it is ending. We are unable to see that. Let me see, I'm going to zoom this one. Yeah, if you just have a look at it once again, you can see the line over here, white line over here. Okay, it is going to end at minus 5357.1 Newton meter. Okay, so this is how the interpretation of the results has to be done. Okay, meanwhile, when you click on the line element results, choose NMIS-C, NMIS-1 and NMIS-3, you're going to get the maximum bending stress variation over the entire beam. Okay, so this is how you are going to do the analysis of your beams. Now what you need to do for me is you need to copy down all the tables. One is for deflection table, other one is a shear force diagram table, bending moment diagram table, maximum bending stress table. So 4 diagrams you need to copy, 4 tables you need to copy, and you need to copy all the 4 diagrams also.